All right, let's get into some newer material involving solvable groups. So we have a theorem. So last time at the end of the last video, we said that if you have a composition, or if you have a solvable group, then you can use, you can get a composition series by just taking commutators. Like you start with the group, take its commutator, then take that commutator. Since it's solvable, that process will eventually end, and you'll get just the trivial subgroup. And also, let's see here, you get each of the, each subgroup inclusion is normal, and it turns out that each graded piece is abelian, and we proved that 2 videos ago. So it turns out that the reverse is true. If G is a group with a composition series G naught going all the way down to Gn, which is E, such that each graded piece, GRI, G, which is GI mod GI plus 1, is abelian, then G is solvable. So in fact, G is solvable if and only if it has a composition series in which each graded piece is abelian. So let's prove this. Let's see here. I claim that DIG is contained in GI for all I, and thus DN G is contained in E, which means that which means exactly what we want, that G is solvable. Okay, so all we have to do is prove that dig is in GI for all I. And we do that by induction. We induct on I. So, let's see here. DI of G, or rather, we're going to start at 0 because D0G equals G, which is contained in G. 0. Okay, so that base case is easy, and induction step is slightly less easy. So suppose DIG is contained in GI. We want to prove that DI plus 1G is contained in GI plus 1. See here, since. So we know that this is an abelian filtration, or it's a composition series in which all of its graded pieces are abelian, so we better use that. And it turns out we talked about last time the fact that we need to use to prove this. Since GI mod GI plus 1 is abelian, the commutator of GI is contained in GI plus 1. We proved that last time. Okay? So then, DI plus 1G, well, this is just the commutator of DIG, and the commutator, okay, so it's a commutator of DIG, and by the inductive hypothesis, so we suppose DIG is contained in GI, and we use that here, and we get this is just d of gi. Okay, but now we use the fact that this quotient is abelian, which gives us this, and then this is in gi plus 1. So the commutator of g, or the di plus 1 of g, is contained in gi plus 1. This completes induction, or rather it completes our induction argument, and so then we're done. So right, you can see as a corollary, G is solvable if and only if it has composition series whose graded pieces are abelian. And we have another fact. Every P group is solvable. Now, this is actually something that we actually gave a proof for in class back a number of lectures ago, but I figured, oh, well, that's really a fact about composition series, so why mention that then when we can bring it up now? And so that's what I'm going to do. I'm going to prove this now, but then let's hear back then when we covered this in class, or during the lecture where we covered this, I didn't have to do as much work in the videos because there was stuff that we covered that I didn't have to include in the lecture, but now I have to include extra stuff here. And this is a long lecture anyways, so this is just making it longer, but let's prove it so that it will be less long. So let's see here. Are we inducting on R? Here, so let G be a group of order P the R. So obviously G is a group, P is a prime, R is some integer greater than or equal to 1. If R equals 1, yeah, we are inducting. So if R equals 1, G contains E is our this is a composition series. With abelian graded pieces. So again, we have another induction argument where the base case is really easy. And the reason this is a composition series with abelian graded pieces, well, it's really just an abelian graded piece because there's just one graded piece, which is G mod E. And this is abelian since if R is 1, order of G is P. And so it's the cyclic group of order P, and so it's abelian, and it's really nice and everything. So we have abelian graded pieces here. So induct on R. Okay, so let's see here. Where are we? So we're going to let Z be the center of G. So we're holding that we're supposing that it holds up to R minus 1, I believe. Right. Yeah. Suppose the claim holds for powers of P up to r minus 1. And then we have to prove that it holds for groups of, so we suppose that for every group whose order is p to the s, where s is less than r, that it's solvable. And now we take a group whose order is p to the r, and then we want to prove that it's solvable. Okay, so here we are, and let's see here. We know there exists some element x in Z minus the identity, and that's because any P group is going to have non-trivial center. And I can't remember if we proved this. Well, I mean, look, if you have a group of order P to the R, then right. It's a fact that P groups have to have non-trivial center, and if I haven't proven that at some point in this course, then it should be not too difficult to prove using stuff in this course. Or it's like an obvious one-sentence proof and I'm blanking on it right now. So anyways, there is some element x in non-trivial element x in the center. X has order p to the s for some s less than or equal to r, right? Because the order of any element has to divide the order of the group, and the group has order p to the r, so the order of x must be p to the s, where s is less than or equal to r. Let's see here. So then, this is getting really bunched up here at the bottom. Then x to the p to the s minus 1 has order p, right? Because if you raise this to the power of p, then what you're going to get is you're going to get x to the p to the s, and the order of x is p to the s, which means that x to the p to the s is trivial, or is the identity element. So this has order p. So the subgroup H, which we're going to define to be equal to the subgroup generated by x to the ps minus 1, is contained in the center, and H, well, it's isomorphic to ZP. So Z mod PZ. I'm just going to write it as Z sub P. Okay? So now, so the order of G is P to the R, and the order of H is P. So the order of G mod H, which we know that this is a group because H is, let's see here, H is contained in the center, so H commutes, so every element of H commutes with everything in G, and so in particular, conjugating any element of H by anything in G will just give you that element of H back, which means that H is normal in G. So actually, let's state that. H is normal in G, so G mod H is a group, and its order is P to the R minus 1. So G mod H, by the inductive hypothesis, or induction hypothesis, I don't know which one it is, which one you say, has an Abelian filtration, right? Because we know that G mod H is solvable by the induction hypothesis, and so it has an Abelian filtration by this theorem, and we're going to call this G mod H is G0 mod H, containing all the way down to GR minus 1 mod H, which equals H. Why did I use R minus 1 there? I guess we don't know for sure that this is R minus 1. Let me just use M. I don't think there's any importance to this. One thing to note is, why do these subgroups look like this? All we know is that these are subgroups of G mod H. The reason that all subgroups of G mod H look like this is by the first isomorphism theorem, because that's how we know what these look like. And so here, of course, G0 through Gm, those are subgroups of G. Okay, so let pi be projection, and let's let Gi be inverse projection of Gj mod H. By the isomorphism theorems, we have we're using J's here, I guess. Gj plus 1 is going to be normal in Gj. And why is that? Let me make sure I'm not going over. Okay. Why is that? This is because the isomorphism theorem that establishes the correspondence between subgroups of G mod H and subgroups of G also tells you about normality. And so let's see here. If we right, so if well, maybe this isn't the isomorphism theorems. We know that Gj plus 1 mod H is normal in Gj mod H, and so if you conjugate elements, in here, let's write it out. Gj plus 1 is normal in Gj because for all G, H in G, so we have Gj plus 1, normal in G. So for all GH in Gj plus 1 mod H, and for all H, and that's horrible notation, but I'm going to stick with it, GH mod H. No, I have these backwards, and because they're backwards, I can make better notation. So the one in the bigger, which one's the bigger subgroup? The bigger one is here, so this is going to be G, so GH, and this we're going to have KH. So we want GKG inverse. This is going to be so GKG inverse H is in GJ mod H, and that's because of this is what happens when you multiply GH times KH times GH inverse, because that's how multiplication works in G mod H. And so then you get this. This thing is in here, which means that this thing GKG inverse must be in GJ. And so what you can prove there is that you use that to prove that, let's see here, this holds for any G in GJ and for any K in GJ plus 1, and thus GJ plus 1 is normal in GJ. So there you go. And by the isomorphism theorems, Gj mod Gj plus 1 is isomorphic to Gj mod H mod Gj plus 1 mod H. All right, and that should be about it, because And so this is abelian. And why is this abelian? Well, oh right, because this is an abelian filtration, so this is abelian, and so this is abelian, and so then taking G and going from G down to H is going to be so our final abelian composition series for G in this inductive step is you're going to start with G and take G equal G naught, go all the way down to Gm, and we've just proven that this is an abelian composition series. But Gm here is Gm mod H is equal to E, so Gm equals H, and so H here, H is ZP, and so H is abelian itself, and just sticking an E on the end here will give you the desired composition series, and so this finishes our proof.